Hi everyone. In this chapter we will be studying relations and functions. In this first lesson we will be looking at terminology. And the first word we want to define is the word relation.
All right, everybody. So we're going to talk about relations and functions in this particular unit. And this has got to be one of my favorite units. I love talking about this because I really do see it as a big step forward in your mathematics. So let's take a look at some definitions here just to start off with, just so that we're all kind of saying the same thing at the same time here. So a relation, okay, between two sets is simply a collection of ordered pairs, okay? Now ordered pairs, remember, being your x comma y, we put them in parentheses here, and the order is important, okay, because we whichever one comes first, we've associated that with a specific set. The second number is associated with the other set, okay, and so those are clearly mapped out in our heads here. Okay, so it's a set of ordered pairs containing one object from each set. So we're comparing two sets. The x is from one set, the y is from another set. Okay, now at this point here, we're not even talking about graphing them. And I know your experience has been that you know that if you got an x comma y, if you got an ordered pair, that's something you can graph. And that is related to this idea of a relation here, okay? It's part of that, but it doesn't have to necessarily be like that. So here we go. So if object x is from the first set and object y is from the second set, which is, I mean, that's pretty standard how we do that, okay? Then the objects are said to be related if the ordered pair x comma y is in the relation, okay, is in that set of points there. So for example, and this is, again, this is nothing new. You have the set of points here, 2 comma 4, 4 comma 8, 6 comma 12. That is a relation, okay, because we've got this. Basically, we've come up with a bunch of ordered pairs. It's all we really need. And we use this little set notation there because, or that's what a relation is. It's a set of points. Okay? But it doesn't have to be like a relationship between numbers. Okay? It can be something like this, boy, comma 11. Okay? And even just one all by itself there, that's a relation. Yeah, it doesn't have to be very complicated, although they can get to be quite complicated. Now, there's lots of different ways of representing relations. Okay? Table of values, you've probably already used that before. Okay, that's a way of representing that relationship. You could graph it, which is, again, that's a fairly natural one when you start seeing those x's and y's there. An arrow diagram. Now this is not quite as common. You probably did something like an arrow diagram really far back in your education, and we're going to pull it back up again and look at it again here because it really is a useful tool for understanding this kind of a this idea of a relation. Equations are great, okay, when they apply, when they work, and in words you can have a description here. Got to be careful with this one though. This tends to be a little bit more difficult because it's a tough thing. I mean, you think about the issues that a lot of us have with word problems. Converting back and forth between English and the mathematical notation, that's not always easy. Okay, but that is another way that we can represent a relation here. And I'm sure there are more. Okay, now we're going to take a look at some examples. Okay, so in this example here, we're going to take this set of points. There's just 3 of them. It's a relation because I've got these ordered pairs, and that's all I need. Okay, we're going to represent it in a few different ways here. Now, to start off with, we're going to take a look at this table of values. And we're going to list the x coordinates here. So that's 1, 2, 3. And then the corresponding y value is going to be 3, 4, 5. Okay, so here's another way of representing. Basically, it's just writing out the ordered pairs, but in a different way, with a little bit of a label on top, make it quite clear. Or we can do this graphically. Okay, bearing in mind that this is our x-axis, this is our y-axis here. So we've got the point 1, 3. Okay, so 1 horizontally, 3 vertically. Or I should say 1 in the x direction, 3 in the y direction, 2 and then 4, 3 and then 5. Okay, now you might be tempted at this point to want to connect the dots, but this is the relation. That's it. There's no other points, so there's just these 3 points, so when you graph it, there's just those 3 points. Don't connect the dots because as soon as you draw a line through that, you imply that all of the points in between are also included, and they're not. Now, but we're going to see kind of a limitation with some of these representations, okay? For example, with the equation, we've got y equals x plus 2. Now, this is good, but it implies all values. Okay? This is not a bad representation of this relationship. Okay? In fact, it's quite clear. In fact, if anything else, it's more clear, it's more directly stated than these two here. But these two right here give us a sense of the size of this relation. There's only 3 points here. This one here could be infinite for all we know. Okay? Now, in words, and in words we're going to suffer from sort of a similar sort of thing unless you get really wordy, and that's kind of the danger. Basically, our words here are going to describe what we're seeing in the equation. And we say it like this: the independent variable, oh sorry, I wrote that wrong. In my head I was going to do that slightly differently. I'm going to swap that around here. Let's do it like this: the dependent variable. Okay. Now the dependent variable is what? What am I referring to when I say dependent variable? Well, I'm referring to y. Okay, the dependent variable y. Okay, and I say the reason why y is the dependent variable because we almost always write y equals, and then it's some function of x here. Y depends on what value you choose for x. Okay, now someone's going to say, yeah, but can't I reorganize it so it's x equals? Yeah, you can, but that's not going to be the way that we would normally do that. Okay. Almost always, y is the dependent variable, and x is going to be the independent. So I choose the value for x, and I look at how y depends on that. So what we're seeing right here in this relation is that the dependent variable y is 2 more than the independent variable. Sorry, no, that's right. That's what I want to say. Independent variable. Okay, and we might comma x there. Now that's great. It's basically stating exactly what's going on here. I do want to push you towards the use of the phrase, the words here, dependent variable and independent variable. Okay, because in different contexts here, and this is really where we're going here, you won't always use y and x. You can use other variables, and so you're going to have to make a choice as to which one is independent, which one is dependent. Okay, so because what we're analyzing here isn't y equals x plus 2. We're analyzing the idea of a relationship, not a specific relation, but what relations are. And so we don't always have to use x and y for a relation here. Now, we might add in this, by the way, that x is either, or actually, maybe not either is probably not the right word to use there. X can be 1, 2, or 3. In this particular case here, it probably makes sense to limit the values of x here because I've only got the three points here. Now, here, notice that the set of ordered pairs, the table of values, the graph include the data unambiguously. That's exactly right. Like I see exactly what those are supposed to be. Okay? There's no ambiguity here. It's very, very clear. Those are my 3 points here. Whereas the equation and the description may imply the relation applies to much larger sets. This is what we're trying to get at here. However, the bonus to this is that the relationship between those two sets there, the x and the y, is very clear. You might have to look at this for a little bit before you see what that relation is. Okay, so if I was to add another point to that, like if I was to say x is equal to 4, okay, I mean, would you know right off the bat that that's going to be 6 there? Now maybe you would, but we could certainly come up with a far more complicated set here where you would not clearly see the relation here, but you would in the equation. So there's some bonuses to all of these, and there's some drawbacks as well. Okay, so now in this example here, we're still going to be looking at representations of relations. Okay. And I should probably say the reason why we're looking at representations and we focus on this is because you can learn things via the representation. Sometimes by simply changing the way we write things, you might get a clearer picture of what's going on. We saw that in the previous example. Maybe listing the points doesn't give you a really clear view of what the relation is between the x and the y. However, I do get a clear view of, like, for example, how big that relation is, how much it encompasses. But there's other ways of writing it here. So, and again, it doesn't always have to be a numeric one, just so that we can focus on this. This isn't always about objects being mathematical. They can be like an athlete and their particular sport here. So you can see this. We got Jennifer Botterill, ice skating, Jennifer Jones, curling, Jeremy Witherspoon, speed skating, and Jonathan Chichu, ice hockey here. So describe this relation in words. Okay, well, the relation shows the association from the set of athletes to the set of sports. Okay? Now, it's the relation, by the way, think about it like this. This is just a list of athletes. This is just a list of sports. The relation comes in having these two side by side. Okay? That's the relation right there. The idea that we're associating athletes with a specific sport here. Okay? So the real key word here is the word association, from the set of athletes to the set of sports. Two sets there. Okay. Now we could set these up as ordered pairs. This is this is kind of awkward to do with names here, but you can see it's basically the same as that table of values here. Okay. There's our first one right there. Okay. There we go. Curling, and with this Jeremy in the speed skating there, and Jonathan in the ice hockey again. Okay, so anyway, this is a little bit more awkward to do with objects like this, but totally possible. Now notice that it wouldn't make sense for us right now to swap these two. Okay, so for example, we wouldn't write speed skating, comma, Jeremy, because that doesn't make sense, not based on the relation that we've set here, that is an association of the set of athletes to the set of sports. This is backwards. This would suggest that this is the athlete, this is the sport, and that's just not true. So order is very important in this kind of an analysis. There are other places where order isn't important, but in this case it is important here. Now here's the arrow diagram that I was talking about before, where what we do here is we take and we draw a circle around this. This is the set, okay, of all of the athletes. This right here is the set of their sports, okay? And then what we do is we draw arrows connecting the members of this set to the members of this set over here. Now, the relation, okay, the relation here is I hope I'm not overusing this word, but the relation here is the set of arrows in this case. The arrows here are what make the relation, okay? This is just another way of looking at it, but this is a good one for some of the definitions that we're going to look at here in just a second, okay?
Now we will introduce some more definitions.
First of all, we've got the dependent variable. I'm going to come back up to here and talk about these things. So the independent variable, I should say, the independent variable of relation is the variable whose values are not altered by changes in another variable. Okay? In other words, the independent variable is the one that we make conscious choices about changing. Okay? In the ordered pairs, there is always the first variable. Okay, it is always the first variable, and it's always represented on the x, or we should say here the horizontal, okay, axis. That's just the custom how we do this. The independent variable is on the horizontal axis. Okay? The arrows here, okay, in our arrow diagram, the arrows point from the independent variable. Okay? So in this particular case right here, in this particular case here, we're going to have, this is our x. Okay, so all of these people represent specific values of the x, and then this points over here to y, where y takes on the specific values equivalent to those sports that they're participating in. Okay, the dependent variable, okay, relation is the variable whose values depend on the values of the independent variable. Okay, and there's really no other way to explain that. That's why we choose the words dependent and independent. So in other words, changes in the independent variable cause changes to the dependent variable. In ordered pairs, it's always the second variable. Okay, it's on the y-axis, or maybe what we should say here, this is the, I was going to write the vertical axis. Okay, and in this case here, the arrows point to I guess I should probably say it like this: the values, maybe not so much the independent variable, the dependent variable, but the values of the dependent variable. Whoops. Okay. So our arrows point from the values of the independent variable to the values of the dependent variable. So up here, athlete, okay, athlete is the independent, sport is the dependent. Okay, because again, what sport gets played depends on who's playing here. Now a couple of other definitions here. Domain. Actually, there's one other definition that we might throw in here, but at this point in time, for this particular definition here, it won't make much sense. I'll throw it down here in a second or two here, but I'll need a different context to really explain this clearly. The domain is the set of all actual values of the independent variable. Okay, so this right here is the domain. These specific people are the set of all of the possible values of x in this particular context here. So this represents the domain of this relation. Okay? I hope that makes sense. So in other words, everything that could possibly be a value of the independent variable, that's what we call the domain. Then we've got the range, which is a set of all actual values of the dependent variable. Now, see, I love the use of the word actual here. Okay, I love the use of the word actual here, because if you really want to get a sense of how this works here, this is kind of like an experiment. Okay, where if you were to compare this to something in a science class here, the domain represents the manipulated variable, or the values of the manipulated variable. The range represents the values of the responding variable. Now here's the other word that we might use here, and that's going to be the word codomain. And this is the set, whoops, I was going to say these, the set of all possible values of the dependent variable. Okay, now the key word here being possible. So when we start to look at something like this, my codomain, okay, my codomain here would be the set of all sports. The set of all sports, because maybe at first I don't know what they play. I haven't got a clue what they play, okay? But then I do a little bit of research, and all of a sudden my codomain gets weeded down to what we call the range, which is the actual 3 sports that get played by these people. Okay, so that's how I want you to think about it. This makes a lot more sense in a mathematical context, and you'll see this in a little bit here when we start to pull these things out here. But the codomain is all possible values. The range is the actual set of values of the dependent variable. Okay, and if the same value is listed more than once in either the domain or range, we only refer to it once here. With when we start talking about sets, one of the rules for sets is that the repetition is not necessary. You don't need to write something twice if it shows up in the set. So that's all we got to do here. So anyway, I hope that makes a bit of sense. We're going to take a look at another example here in just a second. Yep. Okay. So what we read here for this example is this table shows the masses of different numbers of Canadian quarters. Okay, so we've got numbers of quarters. We just keep adding quarters. We go from 1 up to 5 here. And then the relation is pointing the number of quarters to the overall mass. Okay, now you don't necessarily need to write those arrows in there, but I'm just trying to give you a sense of what's going on here. That the relation that we're trying to build is found in the comparison or the association of that number with that number right there. Okay, now the mass of the quarters, okay, as it says right here, depends on the number of quarters. Okay, it doesn't. You could argue it the other way around if you really wanted to, but it would be awkward. Okay, that you'd really have to kind of struggle with that, fight with that to make it work. It's far more natural to say that yeah, the weight or the mass, we should say here, of those quarters depends on how many you're throwing in there. Notice that the domain is just the set of these values right here. Okay. Now the codomain Okay, if I want to think of it like here, the codomain, now we already know that we're talking about the masses of objects here, so it would be like all positive values here. All positive values. I mean, it could be anything at all here. But as soon as we start doing the experiment, no. These are the specific ones that we're getting, okay? I'm not getting 4, I'm getting 4.4, not 4.5, not 4.3, 4.4. Okay, and then we jump up to 8.8 and so on here. This is the specific set of values that I'm getting. That's my range. Okay, and notice there's something interesting about this data, and we're going to talk about this in a second here. Notice there's no partial quarters. Okay, in here, my domain is simply the numbers 1, 2, 3, 4, 5. There's no 1.5, no 0.3. Okay, it's just these numbers, these just nice whole positive numbers here. Okay, good. Now in this example here, we're being asked to state the domain and range of the following mapping diagram. Okay, now you probably can't see that. So let's get in a little bit closer here. So this is what we got here. The relation here, remember the relation is the description of what the arrow is doing. This is the number of players on a team for, and then they give you obviously the sports here. So right here, this is going to be the number of players, and this is going to be the sport, I guess. So I guess what they're doing here is you've got, think of it like this, we're looking at the number, maybe you're like a camp director or whatever, you're looking at the number of kids you've got to work with here. You're thinking, okay, well, what sports can we reasonably play with this number of people? Okay, and so here, look at the numbers we've got. We've got 5, 6, 9, 11. Now, when we're talking about number of people, you can't have fractional numbers of people. Okay, it's not 5 to 6 or like 5 to 11. That doesn't make any sense whatsoever in this context here. So what we'll do here for our domain, and remember the domain is all the specific values of the independent variable. Okay, so this is kind of what we got control over. This is what I have to decide these values based on these values. Okay, but my domain is going to be the set of numbers 5, 6, 9, 11. And that's it. Okay, the range, remember now, the codomain would be all possible sports here. Could be anything here. But maybe there's some restrictions as to what we can do here, and so very specifically, these are the ones that we point to. And our range here is going to be baseball. Okay, I'm going to run out. Yeah, here we go. I'm running off the screen here. Basketball, hockey, soccer, and volleyball. Okay, so there we go. That is the specific set of values that our relation points to. Now, one little thing to point out here before we move on, and it's something we're going to come back to. Notice, for example, here that 6, if we've got 6 people here, we got a little bit of choice. We could play either hockey or volleyball. Okay? It's sort of interesting that this right here has a couple of different options that it points to. If we look back to the previous example here, notice that wasn't true. That every time you had a specific value in here, it pointed to a single value in the range. Okay, again, remember our purpose is not, in this chapter, is not specifically to look at the relation that we're setting up here, but we're talking about relations in general. And so this is kind of a qualitatively different relationship. This one goes from here to here, here to here, and there's like 3 won't give you 2 different masses here. But here it is possible, for example, for the number 6 to give me 2 different options here. And it's interesting, and we're going to talk about that, what that means in a little bit. Okay, now we're going to take a look at example 5 here that says represent the relation given below in the table of values. Okay, so here we go. We've got this table of values here. We're going to represent this in different forms illustrated below in this table here. So what we've got here is animals, and we've got our speeds, their maximum running speed here, okay? Now, we come over here, let's take a look at the mapping diagram. So in order to do this, I'm going to fill in the set here. So I've got to put the bison in here, the cougar, coyote, the grizzly, and white-tailed deer. I'm just going to write deer here. Okay, and so this is going to form the domain of the relation that we're building here. Now remember, the relation consists of the set of arrows. Okay, so right now this isn't a relation, and me just putting the numbers here, 35, 55, 69, and 48. Now notice I don't need to write 48 twice, and in fact I don't want to write 48 twice. I only want to write it once in that set. Okay, and that's okay because that is a rule of a set. Okay, if I've got an item showing up more than once, I really don't need to write it more than once. Okay, we're just interested in if it's in the set or not here. Now, the relation is going to be the arrows in between. So the bison is connected to the 30, the cougar is connected to the 55, coyote is connected to the 69. Now the grizzly and the white-tailed deer are both connected to the 48. Well, now that's interesting. Okay, this is a type of a relation that we're going to single out here in a little bit. This kind of relation here, if you want to think about it like this, what I've got here is this is like what we might call a many-to-one relation. If I was to write out the 48 two times here, go grizzly to 48, deer to 48, it would be less obvious that this that this relation would have this property where you've got more than one object here pointing at the same object for the dependent variable, basically in the range here. Now, as ordered pairs, now again, this makes it kind of weird to write it like this, but that's okay. You don't really think about this sort of thing being as an ordered pair, but that's okay. And I'm going to put the little set of here. This will be bison, comma 35, comma cougar, comma 55, coyote, comma 69, grizzly, comma 48. Now when we write these as ordered pairs, we have to include that 48 everywhere it shows up. So we got the deer here and then the 48. Got to write that twice because now I'm deliberately just associating those two together. Okay, and that's how I got to write that. And I close off the set of ordered pairs with a brace there. Okay, because remember we're talking about sets here, so I want to include those within the set notation. Then another way I could do this is by using a graph, specifically a bar graph here. Bar graph makes a lot of sense because remember with a bar graph there's no necessity of it being in any given order down here. Okay, I mean, you might put the animals in alphabetical order, but there's no reason for it to be in this order. You could have it in backwards alphabetic order. You could have it in order of how large the animals are, whatever you want. There's no rule for that. Okay, a lot of the graphs that we're going to work with, obviously, we're going to have the real numbers along the x-axis and then the real numbers along the y-axis here, and we'll plot those together. Okay, so what's the domain of the above relation? Okay, well, our domain, you might write it like this: the domain of that relation there, whatever that relation is, not quite sure what we should call it here. We'll just call it R for relation. The domain is going to be the set of, and it's going to be the bison, cougar, coyote, grizzly, and deer. We'll put that in set notation. Now our range, what's the range of the above relation? Okay, whoops, that's not how we do it. The range for that relation, and I'm just calling it R for lack of a better term here, the range is going to be the set of values 35, 55, 69, and 48. Okay? And 48 there, and again, if it shows up twice, we don't really need to write it twice, that's all we need. But it is interesting, and it tells us something when when the domain of the function is a smaller set than the range of the function. Just kind of an interesting idea here. Anyway, there you go. Now we're going to look at some more definitions that you need to be aware of.
At this point, we want to take a look at different types of graphs.
Okay, so now we're going to talk about different types of data. Okay, and although there are two mentioned here specifically, the continuous data and discontinuous data, there's actually one other one that I want to throw in here as we go through this. So continuous data is data that cannot be broken into distinct values. Okay, and basically if you want to, well, here, in fact, this next sentence says it beautifully. It takes on all values over an interval. over an interval. Okay, so you can have these arbitrary endpoints here, but it takes on every value in between, all the real numbers along some sort of interval here. Okay, whatever, it doesn't really matter where your endpoint is, where your what your starting point is, what your endpoint is. Continuous data is everything in between, and that's how you can recognize it. You can have fractional values. That's not a problem at all, and it takes on all values. It's not just that it can be fractional values, but it's all values in this kind of connected set here. Okay, so in this case, the data is modeled with all the real numbers in an interval. And good examples of continuous sort of data values here would be time, height, mass, and so on and so forth. So for example, if you've got you might have a time versus height graph, or sorry, I should say height versus time graph. What you've got here is maybe somebody growing or some plant growing, whatever. Maybe it grows really quickly to start off with and then levels out here. But the point is, it takes on all values in between those two endpoints. That's what makes it a continuous graph. Now compare that with something that's discontinuous. Okay, so discontinuous data is data which is in which either the independent variable or the dependent variable, okay, one or the other, is continuous, but the other one is discrete. Now, what we mean by discrete is discrete takes on exact, specific values, that not intervals of values, okay? Single values, maybe a whole set of single isolated values, but not all the numbers in between. That's what we mean by discrete, okay? Now, oftentimes you'll hear people say that, well, discrete number means like whole number values. Well, that's often the case, okay, because usually you talk about discrete data in terms of, let's say, the number of people in a classroom, the number of animals, maybe you're buying tickets, the number of tickets you've got for some concert or whatever. You can't rip those things up because when you've got a fraction of a ticket, you don't have a ticket, okay? So a lot of times, yeah, we're talking whole numbers, but it doesn't have to be whole numbers. It could be like money. Money tends to be discrete, because it's broken down in the smallest unit of money that we use is typically the penny, okay, the cent. Nowadays, of course, we do a lot of rounding and whatnot because we don't have the penny in circulation anymore. But yeah, usually the smallest value is that single cent there. And so money would be discrete. So in this case right here, we're talking about a case where we've got two variables here, one of which can take on any value, but the other one doesn't, takes on specific values. And so, good example of that, and I like what's being graphed here because it does a wonderful job of illustrating this. Something like hourly wages, okay, or even charges for fuel. Now, I'll explain that in just a second here, but hourly wages. So just take a look at this. So let's say that you're working and you get some money. Now, if you don't work at all, you get nothing. But as soon as you start working here, okay, or let's say I should say it like this. Let's say you work for the first hour. You're not going to get paid. Okay, you're going to get nothing for that first hour. But as soon as you've worked an hour, boom, it jumps up here. Now you get, you've earned $3. You've earned $3 until you're done working 2 hours. Then boom, you've earned $6. Now, your employer does not give you all the different values in between. It's not like the graph kind of swoops up where at any given point in time you can stop and you'll get a certain amount of money there. Nah, that's not how it works. Okay, that's how much money you've earned, and it jumps up. There's this jump here, which is what we call a discontinuity. Okay, continuous graph is nice and smooth, no little holes in it. This is a discontinuity. Okay. Anyway, so this is a good example. Fuel is the same way. When you purchase fuel, just think about it. You squeeze the handle, the fuel flows into your vehicle. But volume is a continuous sort of a data value. You can chop that off anywhere you want, from 0 liters to, let's say, what is like a 70-liter tank or whatever, right? You can put any amount you want in between 0 and 70. However, when you pay for it, you're only going to pay in the discrete lumps, the pennies. Okay, you're not going to pay in terms of fractions of pennies there. You're going to pay, the smallest amount will be pennies. And so you've got this little thing where the graph jumps up kind of like this. Of course, much smaller little interval down here, but yeah, it's going to jump up like this. So now I want to give you an idea here. Let's say you've got a continuous graph. Just want to compare these things for you here. A continuous graph might look something like this. Now maybe I'll do my example before here. Let's say that you've got, this is time and you're graphing someone's height. So once again, maybe the graph goes something like this, whatever. But it's all connected. From this point to this point here, it's all connected. It's all values in between. That's a continuous graph. This one right here, this is discontinuous. Okay, it's got points where it's all connected along an interval, but then there's these jumps. Okay, there's these bumps that we're seeing here where it goes from one value immediately to another without crossing over anything in between. Now, compare that to what we might call a discrete graph. And let's say that we've got a number of tickets sold and then the price. Well, that's going to look like this. It's just going to be this set of dots, okay? Because you can't sell fractional tickets. And then the price that you get here, okay, because you don't have anything in between there, it's just going to jump from there to there to there to there to there. So in this case right here, this would be a discrete graph. Okay, because the number of tickets really does limit the values here that it takes on between it. You're not going to get any fractional tickets. You're not going to pay fractional price there. Okay. Anyway, so there you go. I hope that helps make sense of the different graphs here: continuous graph, discontinuous graph, and a discrete graph.
In this next section, we're going to introduce the extremely important idea of a function.
Okay, now we're going to take a couple of minutes and we're going to talk about a really, really important idea in mathematics. And in fact, for most of your high school experience and even most of your university experience, when you're working with equations and whatnot, you're going to be working with functions. It's not often, unless you go looking for these things in particular, would you study something that isn't a function. Okay? Now, a function is simply a relation that is either one-to-one or many-to-one. Now, I've already kind of hinted at the many-to-one here, and I'm going to come back here. I want to talk about a couple things here. So take a look at this. This right here is a one-to-one relation. Okay? I've got one item in my domain. It's related to a single item in my, or actually, sorry, this is a really bad example for that. I'm sorry, this one here is actually also many-to-one. Sorry, that's not the one that I wanted to look at here. I'll show you a one-to-one in just a second here. Sorry, it was the other page I wanted to jump to. But I'll take this opportunity to discuss this as well, though. This is many-to-one, and the reason for that is because if I was to write this out, and I should have looked down here real quick, if I was to write this out as a mapping diagram, notice that these two here, Jennifer and Jonathan here, are both pointed at ice hockey. So I've got multiple values pointing to a single value in the range. Okay? Now, I'm okay with that. We are totally okay with that. We also like one-to-one. Now, here's the one that I wanted to point to. Sorry, that was this guy over here. This was with the quarters and the mass here. This is a one-to-one relationship. Every value in the domain points to a single value in the range, okay? And like every value in the range is pointed to from a single value in the domain. It's one value here points to one value here, and kind of vice versa. And we like that too. What we don't like, everybody, what we don't like is what we call one-to-many. And let me flip this over here, and I'll give you a little example here. Okay, what we don't want one-to-many. Now, what one-to-many looks like, if I was to come down here and draw this out for you, let's say I had A, B, C, and I had X, Y, Z here. So I like the fact that A points to A points to X, not a problem. Love the fact that B points to Y, that's it, not a problem. But as soon as you get something that does this, where one value points to multiple values in the range, that's not good. I don't like that. If you think about it like this, the example that I might use here is, let's say you're doing an experiment. Okay, when you're doing an experiment, the independent variable or your manipulated variable. That's the one that you control, and you're looking for how that affects the dependent variable or the responding variable. Okay, so I do a little tweak here. I notice how it causes this thing to change here. So let's say that I'm doing an experiment, and let's say we're trying to determine the temperature at which water boils, and maybe we've got I don't know, maybe we're checking at a different altitudes or whatever. So let's just say, for example, that we got some people in a room. It's a class of students. They're all doing the same experiment. The room is the same pressure, whatever. But let's say I've got somebody that's got theirs at like 95 degrees Celsius, and someone and it's boiling. Somebody right next to them has got it at 95 degrees Celsius, and it's not. Well, see, that's confusing. Okay, that is really confusing. Where one data value, that input there, the value of the manipulated variable, produces two different responses. That's confusing and requires a very different sort of an analysis here. What we like is when one value produces a single result. That's it. Now, by the way, I would be okay in a classroom if I had somebody who's got it at 90 degrees Celsius, someone at 95 degrees Celsius, someone at 100 degrees Celsius. They were all boiling. And then all of a sudden, wow, okay, now we got to have a discussion. What is it? What else is going on here that's causing these different results here? But if you've got somebody at 90, someone at 90, two people at 90 and getting totally different results, that's really confusing. I'm not sure what's going on there. Okay? So, mathematically, when you've got something that's just one-to-one or many-to-one, we call it a function. And essentially, for every x value, there is only one y value. Now, we've got a wonderful way of determining whether or not a relationship is a function if it's graphed. If it's graphed, it's so easy. We call it the vertical line test. So if you've got a function here, so you got this wavy line here, this relationship between x and y. If you draw a vertical line through it and you're only ever able to hit it once, that's a function. Now, you got to hear what I'm saying. Okay? If it doesn't matter where you draw that vertical line, if you only ever hit this graph once, it's a function. So this wavy line is here, this vertical line dropping down, I draw a vertical line through it, I only hit it once. Now look over here. Here, if I draw a vertical line through it, it is possible for me to hit it twice. Not a function. Here, I draw a vertical line through this, I hit it twice. Not a function. Now let me give you another idea. Okay, so let's say you got a function that does something like, I shouldn't say a function, a relation that does something like this. And actually there is an equation that will generate a graph like this. Now, if I chop it over here, if I draw a vertical line through it, I am only hitting it once. But that doesn't matter because this has to do with possibility or existence. If there exists a vertical line that cuts through this thing more than once, there, then it is not a function. It doesn't matter that somewhere over here I can do it and only hit it once. Okay, right here I'm hitting it more than once, not a function. Other things to look for when you've got like a table of values, what you're looking for is you're looking for the same value in the domain or under the independent variable. If you've got one value and it's related to two different y values or values of the dependent variable, not a function. Okay, so let's take a look at some examples here. Okay, so in this example, we read here that for the following relation, identify the domain range and whether the relation is discrete, continuous, discontinuous there, or whether it's a function. So we're asking a lot here. So here's my domain. Remember, my domain of this thing is going to be equal to the set of values of the independent variable. When I've got a list of ordered pairs, the independent variable always comes first. So here, this has got to be 2, 4, 6, 8. My range is the set of values, okay, of the actual values of the dependent variable, not remember, the codomain is all possible values it could have been, and that's going to be all reals here. But my range here is simply going to be those specific numbers, 4, 8, 12, and 16. Now, is the graph discrete, continuous, or you might even throw in here discontinuous? But the truth is there's no intervals associated with this. Okay, I'm not taking all values from 2 to 4, like 4 to 6 or 8 or whatever. This has got to be discrete. This has got to be discrete. It's just a set of 4 points, nothing else. Okay. Immediately, if you want to think of it like this, a good kind of rule of thumb here is if you've got a finite number of values, it's discrete. Okay, it has to be discrete. If you've got an infinite number of possibilities, then it's very likely continuous or even discontinuous, because discontinuous graphs can have an infinite number of points as well. Now, that's not always true, what I just said there, but it'll be true in most of the questions that we look at. Actually, if not all of them that we look at. Is this a function? Well, let's just take a quick look here. Notice that every x value or every value of the independent variable only shows up once with a single y value. Yep, that's a function. Yes, it is. Now come down here. Again, my domain is going to be the set of values of the independent variable. So 7, 17, 18, 21, and 17. Well, now look at that. I don't need to write that twice, because if it shows up in the set once, that's all I need. So as soon as I get to a point where, oh, you know what, I don't need to write that because it's already in there, that suggests to me heavily that this isn't a function. We'll come back to that in a moment here. The range is going to be just the set of the dependent variables, and I'm going to get 2, 2. Now, it doesn't bother me when it repeats in with the y's. That makes no difference to me. It doesn't bother me that different x values produce the same y value. That's okay, as long as one x value isn't producing multiple y values, which is what we've got going on right here. 17. 17 doesn't know what it's doing. Okay, 7 does, 18 does, 21 does, and look, 21 and 7, they both agree the answer should be 2, but 17 doesn't know what it's doing, and so that's a problem here. So anyway, let's continue with the range here. 3 is another one, 2, actually that's it. I only needed those 2 values right there to give me the complete range. Is that discrete or continuous? Well, I've got a finite number of points, 1, 2, 3, 4, 5, so this has got to be discrete. But this is not a function. Okay, this is because of that 17.2, 17.3. All right, so this example, we are reading here for the following relation, identify the domain and range, okay, whether it's discrete or continuous or discontinuous, and whether it's a function. Okay, so my domain is going to be the set of values from where the arrows are pointing. Remember, arrows always point from independent variable to dependent variable. And so what do we got here? We got 5, 6, 9, 11. Okay? My range is going to be the values that the arrows point to. And so what do we got here? We got hockey, volleyball. Oh, my handwriting this is going to be too big. Oh boy. Okay, well, we're going to keep going here. Basketball, baseball, soccer. Not enough room. But anyway, there you go. There's your whole range here. Now, is this a relation or a function? Well, now let's just take a look here. If this is going to be a function, okay, then every point in the domain should know exactly what its value, the resulting value is. 5 goes to basketball, 9 goes to baseball, 11 goes to soccer. 6 has no idea where it's going. Goes to both hockey and volleyball. This is not a function. Okay. The best you can say here is that it is just a relation. Now, I don't want you to get the idea that this is opposite. Okay, when it says relation or function, I don't want you to get the idea that those are mutually exclusive ideas, because a function is a special form of relation. But if it is a function, you would say function, and if it's not, then the best you can say is it's just a relation here. Is this discrete or continuous? Well, are there any intervals that are possible here? And actually, you should see right away, that doesn't make any sense here. Number of players has got to be a whole number. And because these aren't numeric, there's no way to have kind of a smooth transition from one to the other. So this has to be discrete. Okay, there you go. So in this example, all we have to do here is identify whether or not we're looking at functions or not. Okay, so we're going to apply the vertical line test here. Now notice you've got a set of points here. This graph is discrete, but that doesn't, whether it's discrete or continuous or whatever, that has no bearing on whether it's a function or not, because look at this. I can draw a vertical line through here. I hit those 2 points. I can draw a vertical line here. I hit those 2 points. This is not a function, so no. It's a relation, not a function. But here, it doesn't matter where I draw that vertical line, everybody here is slightly offset. Yes, this is a function. Every x coordinate here, every value of x knows exactly what y coordinate it's producing. Okay, there's no indecision there. Here, same sort of thing. Just take a look. No matter where you draw that vertical line here, yeah, you're only going to hit that graph once, so yes, this is a function. But over here, it should jump right out at you real quick. This is not a function. I can draw that line right here. Now, it doesn't matter that if I draw one here and draw one here, I only hit the graph once. That doesn't make any difference, as long as it is possible at some point to draw a vertical line through it and hit the graph more than once. Not a function. Okay, come down here. Vertical line. This is a great one. This is an example of, this is the only straight line that can't be a function. A vertical line, if you draw a vertical line through it, you hit all of the points. This is not a function. It doesn't exist anywhere else. That's it. Okay, here. Now, when you're looking at a table of values, the only way that this could cease to be a function is if you had repetition here, pointing to 2 different numbers here. Now, it doesn't bother me that all of the results here are 5. That makes no difference to me whatsoever. If I was doing an experiment and as we adjusted the one variable, we always got the same result, well, that is a result. It's not confusing. You might wonder, like, why are we getting the same result all the time? But that's not such a bad thing. But if you had, like, if this was 1 and 1 and it was producing 5 and 6, okay, that's a problem here. So this is a function, okay? The values here are only showing up once, and they're only producing one value as a result. When you're looking at a set of points here, again, we're looking for repetition of the independent variable, giving you different values for the y coordinate. Now, again, it doesn't bother me, and this is the trap here. This is what they're trying to get to see if you're going to get confused by here. Notice that you got the point 2, 3, and 4, 3. Well, those are each producing 3s. Yeah, but that doesn't matter. It doesn't matter if the results are the same. What matters is if the same input produces different results. So the fact that 2 gives 3, 4 gives 3, not a problem. As long as 2 isn't giving 3 and then something else here. So yep, this is a function. These are usually pretty easy to work with. When it comes to words, now you got to really think about it. Let's say the dependent variable is equal to the positive and negative values of the square root of the independent variable. The positive and negative values of the square root of the independent variable. So let's just think about that. So let's grab a number there. Let's say 9. And I grabbed 9 because I'm lazy. So what we know here is that y is equal to the positive and negative square root of whatever the independent variable is. Well, the square root of 9 is 3, but then what we're saying here is that we're going to get positive 3 and negative 3. So I am getting for one value of x, I am getting 2 values of y here. This is not a function. Okay, a little bit more difficult when you use words, but not impossible. Okay, so in this example, okay, we read here that the table, we've got here, the table shows the daily rates for emergency medical coverage while traveling outside of Canada for 14 days. Okay, so we got people's ages right here and how much it's going to cost daily, assuming for like medical coverage, yeah, for just the insurance there. Okay, so why is this relation also a function? Okay, let's just take a quick look at it. Okay, we're looking down here at the age right here, and you're noticing that every age only shows up once. Okay, so for every value, for age, there is a single value for rate. And actually, that's just as it should be. You'd be really upset if your age produced different rates. And then you'd be like, okay, well then what's going on here? How can I get the cheap one, right? What's the dependent variable? Well, the dependent variable is going to be the rate, okay? Because that is going to depend on the independent variable, which in this case is going to be your age, right? Okay, because the amount they charge you is going to go up depending on your age because you're more of a risk. Write the domain. Okay, now this is interesting because the domain deals with all the possible values, okay, of the independent variable here. Now, when you take a look at a chart like this, the chart suggests that it starts at 49, ends at 85. Okay, now it looks like you've only got this this finite number of points here, but the truth is, if you're 50 years old, there's a rate for you. Okay, if you're 52 years old, there's a rate for you. If you're 66 years old, there's a rate for you. There's an implication here that it applies to these people as well. This information is here just to give us a trend. We're not going to get every value there. So the domain, now, I got to be kind of realistic here. We're probably being given the lowest value and the highest value here. So the domain in this case here, probably the best I can do here is I will state that it's the set of values from 49 out to 85. Okay, and then actually I shouldn't do that. I'm going to get a little bit more specific here. That's the best I got. If I say more than that, then I'm really extrapolating from the data, and I don't know that that's true. But it's a really safe bet that it's going to be all values in between at least 49 and 85. So I might even include in this that x is going to be an element of the real numbers, implying that it's going to be any real number between 49. Okay, remember, x is greater than or equal to 49, less than or equal to 85. Now, the range. Okay, well, this is a little different because the range is going to take on values here, based on what I'm seeing here, of 2.88 to 19.32. Okay, whoops, sorry, you can't see that. 2.88, 19.32. Thing is, I know that money is actually kind of discrete, okay, because you can't break it down anything more than the penny, or sorry, anything less than the penny here. So this is going to be a little bit harder to write out here. Okay, so this is going to be, let's say 2.88 is less than or equal to y, less than or equal to 19.32. This right here is not 100% correct because it implies everything in between. We might say increasing by, well, I'm not entirely sure what that goes up by without a little bit more data here. So we'd have to work something out here, but I might say this here, increasing by a penny. Okay, it can be any value in between there. I need to know a little bit more information about this before I could write that off for sure. But it's going to be the values in between and equaling 2.88 to 19.32 for sure. I'm just not entirely sure how that works. Is this data discrete or continuous? Well, age is continuous. Money is discrete. So I would say this is discontinuous. Okay. What is very likely going to happen is there's going to be a rate for you being 49, and then when you hit 50, the rate is going to jump up, and it'll jump up, I don't know, like to 290, okay, or 289 or whatever. It's going to jump up in these little discrete packages. Without a little bit more information, a little bit more time here, I don't know. Okay, so I hope you're kind of getting a sense of how this can actually get a little bit more difficult, where it's not just a matter of listing the numbers that you're seeing, but you got to think about a few things. Like in some cases, that's all we did. We just listed off the numbers that we saw on the table. But here, the context implies something more is going on here, and I have to take into account the context when I start to identify the domain and range and figure out whether it's continuous or discontinuous or what? It's a good question. All right, for this example, we read here, for each of the following, identify if it's a function, state the domain and range, and I love this little inclusion here, as best as you can. Okay, because that can be a little confusing. Now, later on in this chapter, we're gonna talk about this again, domain and range. We're gonna come back to this idea and talk about how to write it and give you some better tools for writing it. For right now, again, as best as you can. We just saw in the previous example that can be hard. That can be hard to be like specific enough specific enough to get everything, but at the same time without making it difficult. It can be really difficult here anyway to get that worked out. And then identify its discrete, continuous or discontinuous. So here we go. Cell phone charges, minutes, okay, total cost. Now, identify the dependent variable. Well, okay, the cost depends on how long you've been talking here. So the minutes will work like this. Now, in this particular case here, without extrapolating, which is the word we use for going beyond the data that we're given, and very likely that would work here. I mean, if you look at how this is going here, it looks like it's going up by 2s. We go down to 0 minutes, it's going to cost nothing. I mean, it looks like it's going up $2, every 10 minutes, or $1 every 5 minutes, or whatever. But we're going to stick with this right here. But I think it's pretty safe to say that it's going to take on all matter of time in between 10 and 50. So my domain here would be the set, let's just say, of values for time in between 10 and 50. I can't really comment beyond this chart because that would just be, I mean, I'm assuming that the pattern does continue. But like based on what's going on here, I'm pretty confident that there's a steady pattern here. So that's going to be between 10 and 50. And remember, this is a continuous data value. It's going to take on all values in between 10 and 50 there, including. But my range, on the other hand, doesn't. Okay? The range is going to be the set of values starting at 2. The value there for y is going to go from 2 till 10. But increasing again by 0.01. Not the greatest way to write that, but we're not quite there at a point where this is going to make sense yet. Okay? So, yeah, we need a better way of discussing this idea of the range here, particularly when there's okay, we want to take a look at another way of writing that really relies on this idea of the dependence of that variable on the independent variable. And we'll get to this in a bit here. Now, is this going to be discrete or continuous? Well, the amount of time you use is continuous, but the amount of money that you spend is going to be discrete. Okay, you can't break it up beyond that. So remember, this is going to mean discontinuous. It's a little bit continuous, a little bit discrete. Let's take a look at this next one here. Number sold versus revenue. Okay, well, the dependent variable is going to be the revenue. Okay, which is really, revenues is going to be money. Sorry. The independent variable is going to be the number sold. And we're talking about ticket sales here. So this is going to be, okay, again, without extrapolating beyond this is going to be 10 tickets out to 50 tickets. But the implication here is that, remember, the number of tickets sold is discrete. And so I'm going to add to this that x is going to be an element of the integers. Okay, it's going to be all integer values between 10 and 50. That way I exclude the fractions, because they don't have fractions of a ticket here. Okay, now remember, we've probably talked about this earlier here, but we use Z typically to refer to integers. I know some people are going to use I, and that's fine for this level of math here, but the truth is the symbol that gets used for integers is Z. I just want you to know that. I don't want you surprised when you get to university here. The range, okay, well, range is money. Okay, range is going to deal with money here. Now, in this case here, I'm going to be a little bit more specific, and I'll show you. We're going to kind of hone this a little bit here. Notice that we're going up. We got $20 for 10 tickets, $40 for 20 tickets. Oh, well, wait a minute. How much is a ticket? Well, the tickets are going to be $2 each. So this is going to be from 20 out to 100, but now I can be a little bit more specific here. This is increasing by 2. Okay, and again, this is not a great way to write this, but this is now a much better way of writing the range because that actually hits every single value. Okay, and I can say that because I could tell right away what that was going to be. Now I could do something similar up here. It was just going to take a bit more work to figure that all out, write that out there. Okay. Actually, in fact, I might just do that here. Let's just take a quick look at this, and we'll come back up here and finish this. Because if I go from 10 to 20 minutes, and I'm going up by well, no, see, but the problem is with this. The problem is with this one here is that you can talk for a fraction of a minute. Down here, you can't buy fractions of a ticket, and so that's why that one worked out a little bit nicer. Is this one here going to be discrete or continuous? It's going to be discrete, okay? Because, yeah, there's no intervals. In either one of these things, there's no intervals of values that you're going to be working over. Plant growth. Months, height. Okay, identify the dependent variable. That's going to be the height, okay, because how high up it goes depends on how long it's been growing. The independent variable will be time, which in this case is months. And now here, what's the domain? Again, without extrapolating, without going beyond this, I'm going to say from 1 out to 5, including here. Now, and actually I should probably write it like this. I can now state that x is going to take on an element of the reals, because it can be any value in between there, any conceivable value in between 1 and 5, and that would work out good here, or well. The range is going to be the set of values from 0.5 out to 6. And in this case, I will also say that the value of y here can be any real number, because it's going to take on all conceivable values between 0.5 and 6, because height is also a continuous value here. So, when I take a look at this graph here, is it going to be discrete or continuous? Well, and the answer in this case is it's going to be continuous. So we got 3 examples covering kind of the 3 different types of graphs here. I hope this makes sense to you.